maybe we can start. Okay, Isha?
Okay,
Okay.
sure. Let me
Okay.
switch off
Now
the
let me
video
start.
first.
Okay.
Okay, sure.
Let me start. Okay. So welcome to Majorana-Raychaudhuri seminar series today. Today our first speaker is Anisha from University of Glasgow, UK, and the title of her talk is Higgs effective field theory: New physics effects at colliders. So Anisha, the screen is yours.
Okay, thank you so much. First of all, I would like to thank the organizers for inviting me to present my work. And talking about the talk, it is going to be based upon these three works that I did in past 2 years with my collaborators at Glasgow, Granada, Daisy, and Durham. So before starting, I will chalk the plan of my talk. So I will start with quartic Higgs gauge couplings, and I will discuss that why we need a different framework beyond standard model so that our predictions are consistent. And then I will discuss the framework of HEFT, and I will discuss the constraints on these quartic Higgs gauge couplings using the single Higgs data. And further to just put constraints on higher dimensional operators in HEFT, I will use these off-shell measurements. And in the final part, I will discuss this BSM HEFT scenario where I will discuss the interactions of the BSM particle, which is ALP, with Higgs. Okay. So I'll start with these quartic Higgs gauge couplings. So experimentally, such HHVV couplings, these are probed in di-Higgs production via weak boson fusion. And these are the three Feynman diagrams which are responsible for it. But VBF is very statistically limited channel as the production cross-section is around 1.7 femtobar. And gluon-gluon fusion has the largest cross-section for di-Higgs. In VBF, there are these three couplings which are shown by colored blobs over here, which are predominantly probed. So first is basically HHVV coupling. And the green one shows the HVV coupling, and this orange one shows triple Higgs triple Higgs interactions like HHH. And because of very limited cross sections, these couplings are very weakly constrained. So to enhance this, usually in experiments, a kappa framework is followed where a coupling modifiers are defined, which are basically uh, deviation away from the standard model. So this is how the kappa parameters are defined in kappa framework. If we talk about these parameters like kappa V, these are constrained from single Higgs case. Kappa lambda basically has better sensitivity from gluon-gluon fusion, and therefore it only leaves us that kappa 2V is the only one parameter which has unique sensitivity coming from vector boson fusion. Okay, so studying these deviations are very important as these can induce changes in the cross section. These can increase the di-Higgs production rates, and also deviation of these will tend to the deviations in single Higgs interactions with the gauge bosons, that is HVV, and which can also point us to the indicator of new physics. Okay. First of all, we'll discuss the effect of modifying these couplings in a theoretical framework of standard model. So generally in experiments, when such couplings are studied, you modify one couplings while keeping other couplings to be standard model consistent. So we'll only consider the modification in HHVV coupling, and we will keep HVV modifiers to be standard model life, that is to be equivalent to 1. So before discussing these, like the constraints, we need to look into electroweak precision constraints. Now these couplings are flat rescalings. There are no momentum dependencies over here. So your delta S and delta U parameters are 0, whereas delta T parameter looks like somehow like this, which also corresponds if there is delta T non-zero value that corresponds to custodial isospin violation, which we can clearly see if your HHZZ coupling is different from the HHWW coupling. Now, looking into the present constraints that we have from GFITR, these kappa 2Z has to be equivalent to kappa 2W at the order of 1.5% level for cutoff regulator of about 10 TeV, sorry. So by imposing kappa HHWW couplings equivalent to HHZZ coupling deviations to be same, we can put delta T equivalent to 0 so that we can impose custodial invariance into our theory. Now we will consider this in our further constraints. We will discuss that we will consider kappa, HHWW couplings equivalent to HHZZ couplings. Now, at the leading order, the first thing we can discuss the constraints on these modifications using the unitarity. So for unitarity, we consider this HVL scattering, and as per the unitarity criteria, the zeroth order partial wave has to be the less than 0.5 here, like the real part of the zeroth partial wave has to be less than 0.5. And on the right hand side, I've shown the constraints where zeta 2 is basically the deviation from 1 of these HHVV couplings. And on the x-axis, I have shown the scale of unitarity breakdown. And on this plot, I've also put the constraints which are available from Atlas and CMS. We can clearly see at a particular scale, these constraints that we get from unitarity, they are quite weak as compared to the already existing bounds. Therefore, now if we move to one loop order, there we see like if we want to study the radiative corrections to H to ZZ in a very journal gauge, we will see that, and we modify this HHZZ or HHVV couplings, we will see that there are these diagrams at one loop order, which contributes to the radiative corrections to H to ZZ. And if we consider the one loop contributions and plus we add the counter term in order to obtain the renormalized amplitude as we generally do, we will see that it will still contain a UV divergence. This part is complete the UV divergence. We are not able to fix it. And this will be able to, this will be like proportional to zeta 2, this coupling deviation. And if this zeta 2 is not equivalent to 0, still the gauge invariance, we will see the gauge invariance is broken because of this zeta z sitting over here. And even if we introduce a bare HCZ coupling, then also we will not be able to relate this HCZ coupling to any physical observable. So gauge invariance is completely, like gauge dependence is completely spoiled over here. So why this happens, the first instinct why this happens is because of the reason that in standard model, your phi is the doublet. And due to the gauge symmetry, if you expand the kinetic term of phi doublet, we will see that these HCZ couplings are fully correlated with HHCZ couplings. And which, like, therefore, if we modify one coupling while keeping other to be fixed, that spoils completely the gauge invariance in our theory. So, like, because of the weak unitarity constraints at leading order and this broken gauge invariance at one loop order tells us that we need a better theoretical framework in order so that we can compare the Atlas and CMS measurements. So what our framework requires, it requires two conditions: that we don't want any correlation inconsistencies like that we saw in standard model between HZZ and HHZZ couplings. And we want the interactions of Higgs with the gauge bosons as to be completely independent, like we want them to be free, so that we can find the constraints on HHVV couplings in the light of HVV interactions or in the light of like single Higgs data. So the one framework which tells us and we can get away with these problems is Higgs effective field theory, where the standard model Higgs is not part of the phi doublet. It's a singlet field, and there is, because of being singlet, there is no limit on its interactions with other standard model fields. So before starting with Higgs effective field theory, I will give you a very brief recap of effective field theory. So effective field theory is a model-independent way of describing in any new physics, and which is generally encapsulated in these higher dimensional operators. And by comparing the experimental data with the theoretical predictions, we can get to know about the new physics. And we don't need to know and the UV theory, it's just a model-independent way. Now, for the phenomenology related with the Higgs sector, there are two types of EFTs possible. One is the SMIFT, other is the HEFT. SMIFT is very, very famous in the literature nowadays. And in SMIFT, if we talk about the basic structure, Higgs field and Goldstones, they are encoded in a doublet kind of a structure. And effective Lagrangian is written before spontaneous Petri breaking with standard model Lagrangian and with higher dimensional operators then written on top of standard model Lagrangian. And for the case of HEFT, Higgs and Goldstones, they are completely independent. They are just treated separately. Higgs being a singlet, and Goldstones, they are written using as a bidoublet of SU2L and U1Y. And the effective HEFT Lagrangian is written on top of electroweak chiral Lagrangian with extra Higgs added to it after spontaneous Vitry breaking. So a lot of works has been done till now. A lot of works are available which discriminate both these EFTs while considering SMEFT, like bottom-up approach as well as the top-down approach. So our main framework is HEFT. We'll now move to the HEFT framework. So what happens, as I already mentioned, that standard model Higgs is not part of the phi doublet. So the interactions of Higgs with the other standard model fields are written using generic polynomials, which are written in powers of h. And Goldstones, they are written as a bidoublet. And using this nonlinear parameterization, like U, it's written using this U matrix, which is an exponential parameterization. And gauge bosons, if I talk about, they are written using the covariant derivative. And the physical gauge bosons appear in the similar manner how they appear in the standard model. So using these pieces, Heft Lagrangian is written. And the leading order Heft Lagrangian somehow looks like this, where the first two terms are basically the field strength tensors. And if I talk about the third term, this is the main important term, which gives the interactions of Higgs with the gauge bosons as well as the Goldstone bosons. And if I talk about this in a bit more detail, here this curly FH is basically this generic polynomial written in powers of h by v. Here, if these zeta1 and zeta2 are the new physics parameters or the Heft parameters, which corresponds to these kappa v and kappa 2v deviations. And this fourth term is the kinetic term of the Higgs. VH is the potential. L fermion is um, the kinetic terms of the fermions, and Yukawa is basically the interactions of the Higgs with the fermions. So in our framework, it is written again using the U matrix. Here, these curly Y's are nothing but again they have the similar structure like these FH, and this FH curly FH is also known in the literature as to be flare function. So I'll call this FH as to be flare function next time if I'll call this if I have to call this. So here, like in the similar notation, these curly Y's are written. And for our analysis, we have not considered any new physics deviations to the Higgs interactions with the fermions. So we have taken A1F to be 0. And in this part of the work, I've also considered like light quarks as well as the leptons to be massless. We have not considered them in our analysis. Okay. So our main aim is that we want to find the bounds on kappa 2v using the single Higgs data that will basically prove the correlations between kappa v and kappa 2v in Heft framework. So before starting with these one loop effects, we need to know how the renormalization is done in Heft. Heft has a different way of dealing with divergences. So in order to get away with the divergences, we need higher dimensional operators because when we write the one loop structures pairing with the leading order Lagrangian, there appear new structures which cannot be handled with the usual counter term, which is written using like how you write in standard model. The divergences can't be get away. So for that, we need to add higher dimensional operators. So our total Lagrangian looks like the leading order Lagrangian plus these higher order dimension operators that we add in order to capture all the divergences. And also, these higher dimensional operators also serve as a tree level contribution to the different amplitudes. So for the one loop computations in our analysis, we have validated that gauge independence is completely followed. And so we have done the analysis in RZI gauge. And for the on-shell renormalization conditions, we have followed, like for the electroweak parameters, we have tried to find the 2-point functions and 3-point functions and followed the on-shell renormalization scheme for them in order to find the field redefinitions and mass renormalization parameters. Now for the renormalization of the Heft parameters, let is AIs and zeta i's, we have followed mass MS bar renormalization scheme, and these two things, on-shell and off-shell, mass MS bar scheme is followed, both handled simultaneously. If you want to go into a bit detail how this thing is done, you can follow this paper by Maria Herrero and Roberto Merles. We have done everything in very involved manner. Okay, so now we need the information of higher dimensional operators. So higher dimensional operators are basically, it is being mentioned in the literature that these comes from Appelquist longitudinal basis, which is the basis for electroweak chiral Lagrangian. If we add the standard model Higgs singlet to these interactions, we can get the higher order interactions appearing in Heft. And we need these two entities as well as for in order to define these operators. These are the list of the 16 operators that we consider in our analysis. Okay, so to give you an idea how this one loop stuff is done, I'm going to give you a very simple example of Higgs to WW. So on the left, these are the list of the one loop amplitudes or one loop diagrams which appears for the computation of H to WW. And in order to get away with the divergences, we need, as I told, we need higher dimensional operators as well. So these are the three higher dimensional operators that we require. And this is the corresponding tree level amplitude which appears with these operators. So now to write uh, like the renormalized amplitude, we need this counter term, where the terms in this blue dotted box is the one which is from the usual standard model counter term. Write the 2-point functions and calculate field renormalization and mass renormalization parameters in the on-shell scheme. And this other part, which is in the red dotted box, it's the one which is written from information of this particular parameters. And in order to do the renormalization of these heft parameters, we have to look into the divergences. For example, in the one loop amplitude, we don't get any divergence corresponding to this particular Lorentz structure. So that's why this fixes some initial condition over here for these two parameters. Q square dependent part fixes other two parameters, and Q square independent part fixes this zeta1 parameter in our analysis. So consistently adding the counter term, and we get away with these divergences, and we write the renormalized one loop amplitude for the different Higgs to VV decays and Higgs to like single Higgs decays, if I tell in detail. Okay. So following this procedure, we have obtained Higgs to gamma gamma, Higgs to gamma z, Higgs to WW star and ZZ star, and we have write down the total amplitude. For that, we have after then using that, we have written the decay widths, which are written in terms of zeta1 and zeta2 parameters. And remember that zeta2 everywhere is loop induced. Now to get experimental results, so as to compare, we have defined these Higgs width in terms of the kappa parameters, which are basically the Higgs width are proportional to the kappa squares. We can write the chi-square, and here, if I tell you the information about this chi-square, this kappa I experimental, these are the experimental values of the kappas, and kappa I theoretical is basically the expression which you get in terms of zeta1 and zeta2, and this V is basically a correlation matrix, and the information is given over the box underneath. And in order to just show the improvements that we can see at high lumi, we have also scaled the uncertainties with this naive luminosity factor. And just while considering that, we have ignored the individual scaling factors of statistical and systematic uncertainties. So after incorporating all, we did this zeta1 and zeta2 fit. And this is on the left, I can show you the parameter space. Here we have scaled zeta2 with 1 by 16 pi square, just because we mm, because just to show the loop induced effect. And with the solid line, we have shown the 68% confidence limits, and with the dotted line, we have shown the 95% limits. We can clearly see that the bounds on zeta1 are strong as expected, and the bounds on zeta2, they are very, very loose if we remove this 16 pi square factor from here. So uh, even with now if we translate this using the high limit data, we can clearly see that bounds on zeta1 gets reduced immensely, whereas for the zeta2 there is reduction, but not that much as expected. So, but with this heft framework, one thing we achieved, that we removed the correlations. We considered this kappa v and kappa 2v as to be completely free parameters without incorporating any correlations into them using the theory involved. And in order to report the constraints on kappa 2v, we need to go to the direct sensitivity. So I'll just very briefly, I'll tell you the direct search bounds which are available. So this part of the work has been done by my collaborators. So I'm not very expert on this, so I'm just going to be very quick with these results. So as I already mentioned, this kappa 2v appears from a vector boson, this di-Higgs production via vector boson fusion. So this is the particular particular process that we took with the 4 Bs and the 2 forward jets. So some pre-selection cuts we incorporated for the VBF topologies, that we wanted the 2 forwarded jets in the opposite detector hemispheres with their invariant mass to be greater than 500 GeV. And for the B jets, we have taken their PT has to be greater than 20 GeV. So the events are simulated in MATGraph. So what we saw that and the very dominated background for this VBF topology is QCD multijet production. And after simulations, after generating the events, we saw that QCD multijet background cross-section appears out to be 4.41 picobarns, and whereas the signal cross-section appears as to be 0.086 femtobarns. So we need to work so that we can reduce this background and increase the signal sensitivity. So for that, we considered this graph neural network machine learning method. So for this, I have shown this schematic diagram. We have considered this fully connected bidirectional graphs where each nodes are basically your final states of the particle, which are 4 Bs and 2 forward jets. And each node is connected to every other node using these edges. And every node has distinct features. And we start with some input node features. And using the edge convolutional networks, some message passing layers, we calculate the final node features. And in the end, a binary classifier is there, which just gives you the final probability of the signal in the background. So the training is done in such a way so that in the end, you have the signal probability has to be 1 and the background probability goes to 0. The network performance is shown by this ROC curve. And on this ROC curve, we just take a particular point, which gives you the efficiencies of GNN, which is added in order to get the final signal events, and next of the analysis is done with it. So using these, we got these 95% exclusion contours for the kappa V and kappa 2V. On this, we have also shown the corresponding atlas limit, which is shown by this blue line over here. So our results is in par with whatever experiments are saying from the GNN. And therefore, we can also go to high luminosity effects. And therefore, in the red, we have shown the high luminosity exclusion contours. Now, in our analysis, when we did this GNN, there can be other backgrounds as well as like the electroweak backgrounds, like electroweak production of gauge bosons, and then maybe top processes, which can lead to the same final state. So to incorporate their effects, we reduce the background with a further factor of 25%. And the effect just does not affect much the final region, which is shown by this blue the gray dot dashed line over here. And just to compare these experimental results that we got from GNN over the kappa analysis results, we just overlay both of these bounds over there on the below. So obviously we can see these kappa 2V bounds appear to be very, very bad, which was supposed to happen because we were just inspecting the correlations between kappa V and kappa 2V coming in HEFT framework. And we wanted to write down what will be the effect if in HEFT framework we inform the reach of kappa 2V from the signal Higgs data. So till now, I have discussed the constraints on the new physics parameters which appear in the leading order Lagrangian in HEFT. Now I'll move to the higher dimensional operators. For higher dimensional operators, I'm going to consider this massive electroweak production of gauge bosons. So this is the process like gluon to Higgs to VV. So back in 2012, in this work by Koila and Melnikov, this particular process was used in order to get the model independence bound on the Higgs width. So to describe this in a bit more detail, this is the tree diagram that we consider. This is the triangle diagram that we consider. So for the on-shell region, like when your Q square, like when your on-shell, like your invariant mass is not greater than the mass of Higgs, we can use the narrow width approximation and we can write the total signal strength proportional to the square of the couplings, as well as it depends upon the decay width. But as soon as we go in the off-shell region, when your invariant mass of the Higgs, like the gauge boson pairs, becomes very greater than the mass of Higgs, there in the Bright-Wigner distribution, Higgs width completely decouples, and you can write the signal strength only proportional to these production couplings as well as the decay couplings. So, and in order to determine the model independent bound on Higgs width, these two, we take the ratio of these two signal strengths, just taking the assumption that our couplings do not grow with energy. So these off-shell measurements, they have the potential also to probe the new physics and BSM effects, which was first explored in this work by Christoph and Michael Spanovsky. So we are going to take this off-shell Higgs measurement and we are going to imbibe this in the HEFT framework. But our basic aim is to look into the effect of the operators which can bring out these high momentum dependencies into the Higgs propagator so that we can constrain those. Okay, so in HEFT, as we had, I showed you the list of operators. In that list, there was one particular operator, this A box box, O box box, which has twofold effects. First of all, because in the self energy, it brings quartic momentum dependence, which can be shown by this Q4. And because of the modification to self energy, like we want the on shell self energy, so we have to put a counter term, and so that your pole, the residue, like the residue is 1 at physical mass of Higgs. And after solving the on-shell renormalization condition, we will get this Higgs field redefinition, which looks like this. After combining this with the self energy, and after we take the inverse, we will see that the Higgs propagator looks like this, where we can clearly see the non-trivial momentum dependency shown by this Q square. If I tell you in SMEFT, no such effects appear. Why? Because there is also a similar operator in a particular basis where you can see such effects of quartic momentum dependence, where again you get the Higgs field redefinition factor and you get the Higgs propagator. But in addition, you also get the Higgs vertex effects, and which, if we combine all these effects together in order to study the off-shell effect, we will see that everything cancels. And these momentum dependencies that we saw in HEF does not appear in SMEFT case. Why? Because obviously there Higgs was a singlet and here Higgs is actually encoded in a doublet kind of a structure. That's why. Okay, so this particular operator also holds importance because if we want to look into the HEFT versus SMEFT effects, to look at, we'll incorporate the corrections which appear from the HEFT interactions to this particular amplitude. We included 3 types of corrections. Shown by the red is the HTT corrections, and like the Higgs couplings to the top pairs. And by the gray is the one which I mentioned in the previous slide about the propagators. And with the orange is the Higgs to VV couplings, but with the other higher dimensional operators. So the final amplitude is written using the help of Lorentz factors, like the form factors, where these form factors are the coefficients of the different Lorentz. They carry important information about the different Lorentz structures. So if we match this amplitude to the Higgs to ZZ part, we will see that, okay, so these form factors can be written as a linear combination of different HEFT operators. And we have written the final amplitudes, keeping in mind that we want the linear order of HEFT coefficients in our analysis. And further to simplify our analysis to reduce our problem, we have also considered that our electroweak precision constraints are not violated in our analysis. So these 3 parameters can be related to STUs. So we will put them to be 0 because obviously we expect these parameters to be strongly constrained from STUs. So therefore, we do not consider them in our analysis. And finally, we put these modifications and corrections in this VBF NLO Monte Carlo generator, and we extract the differential cross sections. And here on the right, I have shown the differential off-shell Higgs momentum distribution for Higgs to ZZ process. We can clearly see the sensitivity coming in the off-shell region where Q is greater than 350 GeV. Similarly, for Higgs to WW, we can get off-shell Higgs HEFT effects. Now, to study the quantitative effect of these differential cross-section distributions, we have to incorporate them into a chi-square bin data, which is shown by this expression. Here, Ni is basically the ith bin differential cross-section input with the off-shell distribution. And NISM is the corresponding standard model contribution. Here, systematic and statistical uncertainties includes the effect of the efficiencies as well as the systematic, so that we get away with the other backgrounds as well. Okay, so the physical significance of the off-shell measurements lies in its correlations with the on-shell measurements. So these are the different like Higgs corrections to the Higgs decay widths that we considered. I'll not go into much detail. And using these corrections, we calculated the total Higgs decay width, then we calculated the modified Higgs branching fractions, and then finally using those, we calculated the signal strengths, assuming narrow width approximation. And finally, we put everything in the form of the chi-square. Okay, so now to combine off-shell and on-shell data, we also further assumed, because we saw that there was particular heft operator which brings out different like different effects as compared to what happens in SMEFT. So we tried to bring the correspondence between heft and SMEFT operators. So we saw that in the list of 16 operators, there were like three operators which can be related to SMEFT operators up to dimension 6 using these translational rules. Now to relate other heft operators, we need to go to higher dimension, and to further study the effect of off-shell and on-shell correlations, we consider these correspondences. So we considered the complete chi-square, and we just profiled over the operators which were related to the SMEF directions. And after profiling, we saw that these were the 4 list of operators which got the strongest bounds. And for one such combinations, I have shown the two parameter regions. Like for the case of A box and AH13, we can clearly see, like here, the different lines show the different bounds. Like the orange one are the single Higgs data, red ones are the complete off-shell data, green ones are the WW data, brown ones are the ZZ data, and the blue shaded region is the complete effect. So we saw that the A box, obviously, they get strong bounds from off-shell measurements as we expected. And the strongest impact comes from the Higgs to ZZ. And obviously, to show the impact of high luminosity effect, we also considered these projections and put them into the chi-square and saw what happened there. So obviously, the improvements were there, and we can clearly see the change in the order of magnitude. Okay, so with this, I'll wrap up that. And now I'll come to the one final example where we considered this ALP HEFT framework. Very quickly, I'll tell you what we did. So ALPs, like axion-like particles, are very motivated BSM particles because of their different properties, and different experimental searches are going on in this field. So generally, because of the lack of the discovery, the ALPs can be described in an effective field theory. So a lot of works has been done which describes ALPs in SMEFT framework, which are like for the references, you can go through these particular like papers. And what we did, we considered ALP in a HEFT framework, and we focused on the interactions of the ALP with a single Higgs, like the singlet character of the Higgs. And for the ALP HEFT, you can also, this was first done in this paper by the IFT Madrid group, and we followed their papers and considered the Lagrangian. And what we did, we considered the leading order Lagrangian, which incorporated the leading order Heft Lagrangian that I mentioned before, and the leading order ALP Lagrangian. So leading order Heft Lagrangian looked the same, just the difference is we did not consider this zeta 1 and zeta 2 parameters. And the leading order ALP Lagrangian look like this, where this A to D derivative coupling is the most important one, which brings out your interactions of the ALP with the Higgs and other standard model particles. And these interactions are written by using these curly F2D operator, which is again a generic polynomial. So the important effects of this particular term is that it brings out ALP Higgs C couplings and ALP WZ couplings. So what we did in our analysis, we studied the phenomenological reach of these couplings leading order as well as in next to leading order. So for the leading order effects, we considered these ALP Higgs C interactions, and this was the Feynman rule. So consider this particular two-body process as the most dominating BSM decay of Higgs. We found out the decay width of Higgs to axion Z, and then we considered the most stringent signal strength of Higgs to gamma gamma, and we found the bounds on we considered this, and we got this parameter space for different values of zeta 1 to D, which is the parameter which gives your ALP Higgs Z interactions. And also for the particular choice of one, we saw that using this signal strength, we can find the upper bound on the Higgs 2 actions, the signal like the decay width, which came out to be 0.65, whereas at high Lumi this gets reduced by half. Now, next we looked into the next to leading order effect, like the virtual imprints of ALP, if we put ALPs into the loops. So the first thing was the Higgs 2-point function, and these were the two diagrams. With these ALP insertions in the loop in the RZI gauge, we saw this is the UV divergence. Again, we saw this Q4 quartic momentum dependence appearing. So to fix this Q4 term, we added this O box operator. And to absorb the divergence, we added this counter term to our theory. And we, after solving the on-shell renormalization conditions, we got the one loop renormalized 2-point function. Now, the important thing is that any corrections to the Higgs 2-point function usually can be given using this H hat parameter, which is nothing, but it's like STU parameters only, but at the order of P4 in the expansion. So experimentally, uh, uh, this H hat parameter is, the constraints are available, but this H hat parameter can be correlated or can be written in terms of the double derivative of the signal strength. And using our expression, we can write the H hat parameter like this, where here everything is finite. The Speserino-Weltman functions, they have finite contributions. We can clearly see that A to D and zeta 1 to D is there, which the same couplings are there as we saw in the leading order effect, but here the loop effects are there, as we can see this 1 by 8 pi square factor over here. So for the bounds, we considered the experimental probes of H hat, and for this, the channel was the 4-top production. Experimentally, for the 4-top analysis, H hat parameter has a bound of 0.12. We rescale this into our analysis at 3 at a bar inverse, and this bound came out to be 0.05. And this is the allowed parameter space that we got for different mass regions. We can clearly see for the lighter Alps, it can propagate freely in the loops. So we have better bounds, whereas for the higher masses of the Alp, our H hat parameter actually vanishes. So combining this 2-point function with the Higgs triple Higgs coupling, we can find the corrections to the Higgs pair production. And this can also open up the doors for finding the bounds on the higher terms in the flare function. Like till now, we focused on zeta 1 2D. We can focus on zeta 2D as well. And the next two leading order corrections appearing with the ALP insertions is done again using the HEFT operators. We need to add them in order to fix the divergences appearing with these different momentum structures. And after combining the 2-point function and the 3-point function, we can get the corrected gluon to Higgs amplitude, and we can put them into VBF NLO, and we can get the differential distribution data, and we can see the effect of these couplings on that. I will not go into much detail over there. Simply, I'll turn to the constraints, where we included both the leading order as well as the radiative impact of these couplings. And we saw that we did that for two different regions. First of all, for the lighter Alps, and then for the higher Alps. Now, I forgot to mention, when we did this BSM decays of Higgs, there was, like, for the on-shell decays, ALP has to be up to the mass range of 34 GeV for the process to happen. So the kinematically allowed value of mass of Hexion is 34 GeV. So for that, we included these two mass regions, and we did the complete chi-square effect. So we saw that for the lighter Alps, and this is all for the high Lumi. So we saw that significant effect comes from the Higgs decays, which are shown by the green region over here. And if we even look at the combined effect, this is pulled by the single Higgs decays. And 4-top over here does not give any valid or strong contribution. And zeta 2D is entirely unconstrained. So we now go to the higher mass regime of Hexion. There we saw that, oh, okay, the zeta 2D bounds now, they become now we can see the bounds, and we can include the constraints from H hat parameter over that also. But also, like, while considering these projections, we consider this root luminosity factor, which is obviously we can think that we can get better bounds at the actual run of the high luminosity effect. So with this, I'll wrap up, and I'll tell you, okay, the final conclusions of the three works that I presented. So in Higgs effective field theory gives you a framework where you can treat your Higgs gauge bosons couplings as to be independent to Higgs gauge boson couplings, so that these couplings are free parameters, and you can consider the bounds, like we can consider the analysis how they are done at ATLAS and CMS, and we can study the bounds on kappa 2v from single Higgs decays without involving any correlation inconsistency into them. But the kappa 2v limits were very weak as compared to the LSC sensitivity already present to kappa 2v. Therefore, we need to have direct searches in order to increase the sensitivity to kappa 2v. Now, further, for the higher dimensional operators in HEFT, we took the help of these optional Higgs measurement, where we also our main focus was this A box operator, which modifies the Higgs propagator and brought out these HEFT versus MEFT effects. Now, to further increase the sensitivity, till now we only considered offshore Higgs measurement. We can add more processes like vector boson fusion, and we can add multi-Higgs measurements, which can bring out more HEFT versus MEFT effects. And it can also add us to, like, it can be a promising aspect for to have a complete global fit. And we, in the final part, I studied ALP in a HEFT framework. So we focused on effective Higgs-philic ALP interactions. For lighter states, we saw that the sensitivity was coming from single Higgs measurements. And for the heavier states, the sensitivity was coming from the di-Higgs pair production rates. And also it told us that photop and di-Higgs processes are motivated avenues to look for the new physics. And the higher terms of the ALP flare function like zeta 2D can be an important parameter if we have to increase the rates of di-Higgs production, so that even if it is a pair, so that we can increase the rates of di-Higgs production, like even in future, so that that will be observable somehow at high luminosity LHC. So with this, I conclude. Yeah, thank you.
Okay, thank you, Anisha, for this nice talk. So, if the audience has any question, please unmute yourself and ask. Okay, if there is no question, let us thank the speaker once again for this nice talk. Interesting talk.
Thank you so
Thank you.
much. Uh, can I leave the Zoom